All right, let's get started. So today we have a bunch of things to cover. We will start with some logistics about the final project, since you are all now in teams and should be working on your project proposals. So I just wanted to give like some high-level ideas for project topics to help with your brainstorming. Also note that this is not an exhaustive set of ideas. You could do things that are not mentioned here, but I know we haven't actually covered a lot of applications of language models or language technology more broadly, so just wanted to kind of get you thinking about that. So let's just start with that. So the overall requirements are, for topic at least, are very minimal. Has to be language related in some way. And as I mentioned before, code and multimodal projects are okay. So multimodal refers to, in this case, like language plus something. So this could be like vision, audio, interaction, whatever. So all of these are fine. The majority of your projects are likely going to be about training, interpreting, evaluating, or applying language models in some way. So I wanted to just give some high-level ideas that I think would be reasonable for the final project. So, like, probably the most popular project idea is, choose a task that your group is interested in and try to build a model that performs well on that task. So this is, you can say, improve LM on task X. And so here you're generally going to be working with open weight LMs, so things like Llama, Quen, generally in the 1 to 7 or 8 billion parameter range, depending on your what kind of compute access your group is either has or is able to acquire. So generally here you want to collect a data set first for your task, run some baselines. So this means how good do existing systems do on your task, right? So if I just put my task into ChatGPT, how well would it do? If I put my task into some existing Llama model, how good does it do? So you want to measure, like, is your task already solved, or is it hard for all existing models? What is the room for improvement? Then you probably want to pick a model and train it on your task. And so there are many different ways to train or adapt an existing language model. We will be talking next week about fine-tuning, which is one of the most common. Within fine-tuning, depending on how much compute you have, you can do things like LoRa or Q-LoRa. These are more efficient methods that don't require as much compute. You could also look into reinforcement learning, which we will talk about after the first exam. And there are other kinds of adaptation techniques that you could also look into when you're another thing you could do is prompt optimization, which has become more relevant recently. And that might be useful if you want to stick with mostly closed language models. So once you do that, you want to measure the improvement and do a detailed error analysis. So figure out, what your model is good at, what it still struggles with. This is generally one of the most important parts of your report if you go down this route, is trying to better understand the behavior of the model that you have constructed and how it compares to your baseline models. So to do this, you could measure like systematic error types. What generally happens here is that you and your group will sit down, annotate a few hundred of your model's outputs, and figure out like any common patterns that you see in it, any strengths and weaknesses, and so on, and you will write about that. Okay, so this is very common paradigm that many of these final projects have done in years past, and this year we have some better open models, so you can maybe be a little more ambitious in what kinds of tasks that you're considering. This year specifically, there's other topics that might be worth exploring based on advances in LLMs. So one thing that I think will be quite popular are these kinds of tool using LLM agents. And so in this case, you may not be trying to train one model in particular, but rather build a system that interacts with the external environment. So this could be, last year we had a nice project that built a Chrome extension that would take some information off whatever web page you're on, send it to a language model. I forget exactly what it did, but it was, I think it was some sort of factuality assessing thing. So you can do things like build browser extensions. You can build apps that use LLMs as modules that eventually solve some higher level task. In this case, you're generally going to be using closed models via API, but I would highly encourage you to try some open models to see what the difference in performance is. You'll note that these kinds of systems are generally quite modular, so you might have like an LLM that does one thing, the output is passed to another LLM call, and so on, and chained until you get some final output. If your model is not very good at the task, it has a high error rate, these errors will just compound as you add more and more modules. So generally these things are implemented via closed API-based models, but open models are getting better. That could be an interesting thing to experiment with. Evaluation here is also quite challenging depending on what kind of task you're choosing to focus on. But you should think very carefully about your evaluation. How much time is it going to take? If your task is too ambitious, we will give you feedback to that effect in the when you submit your proposal. Alternatively, if your task is too simple, then we will give you feedback on that as well. But yeah, for these projects, the evaluation is something that your group will need to think about very carefully and spend a lot of time and effort on it. Another line of work is, interpreting a language model's behavior on some task or skill. So we have not talked about any of these kinds of interpretability techniques, but in general, you might want to identify identify layers or neurons or circuits of neurons that contribute to some sort of skill. There are various methods for trying to identify these things. You can then start doing like interventions on the model. So if you know that this group of neurons is responsible for storing some fact, like the, I don't know, capital of Maryland, maybe you can modify those vectors or just deactivate them during the computation of or generation of some text and see what effect that has on the model. So this is similar to some keywords here, like model unlearning is one. Also steering. So if you're able to identify circuits or neurons, you can try and compute some vectors to steer your network in some desired direction or behavior. So that's another kind of project. Another one that's a little more ambitious is implement some sort of new training method for LMs or for some task. So this is a lot more kind of task and group specific. If you already have some ideas on, based on everything we've learned, some new idea that you want to try out, go for it. We will give you feedback on your proposal if it sounds like it has no chance of working or it's already been done, and we can give you some papers to cite. Kind of similar project is reproduce a recent paper. And so this might sound like an easy task, but it's generally incredibly difficult. We obviously don't want you to just go to the GitHub page associated with some paper and then run the code, right? That's not a project. But in these kinds of projects, we really require you to implement your own version of the paper from scratch and see if it works. And generally it doesn't work, and then you'll have to outline, why do you think it didn't work? Maybe you didn't have enough compute to train it for as much as the paper did, or maybe you found a bug in the paper, or whatever. I mean, there's many things that could happen. Again, this, as long as the paper is language-based, in some way it's fair game for this course. Another kind of newer topic that is maybe only relevant this year and later last year is efficient inference. So a lot of the stuff I've talked about above is involving training or building of systems, but now as the models are getting bigger and bigger and the prompts are getting longer, we also have a just as important problem is to make the models generate text as quickly as possible. So we kind of want to explore this, like increase the decoding speed, but preserve quality. So there's a speed and quality trade-off. Some things we'll talk about later on are KV cache optimization. There's a bunch of cool algorithms that you could try here that, again, don't involve, many of them don't involve any additional training of the model, but rather you might have to do some processing or compression of the hidden states that the model has produced to make things run faster. Finally, there's a interesting class of problems revolving around safety, security, jailbreaking. All of these are fair game. So here you might want your model to respond a certain way when confronted with certain prompts. Like if I ask it to build a bomb, I probably don't want it to give me the recipe to build a bomb. However, there's also the other angle, right? If I know that a model has been kind of trained for safety, aligned for safety purposes, I could then take the role of an adversary who's trying to circumvent that kind of training, right? There's also other kinds of interesting security questions with language models, like can you recover private data that they were trained on, or copyrighted data and things like that. All of that is a reasonable topic to pursue for the project. All right, so again, this is not an exhaustive list, but it includes some common projects that people have done in the past, as well as some new ones that if you're interested in engaging with the most recent research, you could try out as well. Any questions about projects? All right, let me check on here. Questions on here. All right, so good. Let us then move on to the topic for today. Oh, another logistic thing. So I'm still working on your next homework. It is an auto-graded homework, and the auto-grader is being annoying. So I hope to release that by the end of the week. And you'll have a couple weeks to do it. Basically, it involves implementing a transformer, training it, and to pass the homework, you need to get some accuracy on a test set. Okay, so let us go back to the self-attention mechanism that we were talking about earlier. This time we are going to see how that mechanism can be extended to support a full model architecture, which is the transformer. But first, I wanted to highlight a couple things about self-attention that we did not cover in the last class, because we were focused on, how the equations work and so on. First, at the end of the last class, we saw that during training time, we can it's really the worst word, parallelize the hidden state computation, right? And so the way we did this is we first computed all the queries and keys associated with the tokens in the sequence. Then we were able to compute those attention scores, right, the dot product between query and key, with just a single matrix multiplication. We were able to then compute the hidden states with another multiplication of those attention scores with the value vectors, right? So the thing is that this makes training much faster than in an RNN, where we have to compute each hidden state sequentially. However, we did not discuss what happens at test time. In test time, you actually cannot parallelize the computations of a transformer. And so it behaves very similarly to an RNN. You have to compute one hidden state at a time. So why is that? Why can we only do this parallelization at training time but not at test time? Yes?
Because during training time, we're only looking at next operations, and you can parallelize all the next operations in one hash and then compute the attention that way. But for test time, you have to basically run the model every single time to take the next operation.
Exactly. We can only parallelize these computations when we know the full sequence ahead of time. So in my training data, I might have a text that says, my favorite LLM is ChatGPT, right? And so I've turned that in my, diagrams from last class into many different next word predictions, right? Given my, I want to predict favorite. Given favorite, I want to predict LLM. Given my favorite LLM, I want to predict is. The only way I can do this in parallel is because I already know the ground truth next word for all of the prefixes in that sequence, right? But at test time, my goal is to generate new text, right? It's not like I have the answer already. My goal is to, solve homework 1 of this class, right? I don't know that in advance. And so the model needs to predict one word at a time. Only when it knows what word it's predicted can it then compute attention based on that word and all the previous ones, and then form a distribution over the next word. So RNNs and transformers, you don't really see much difference in terms of inference time, like test time, speed to decode a full sequence, because you are not given the sequence in advance. Does that make sense? That's very important. So, yeah. Yes?
For training, if you did it in the sequential way, wouldn't that be more accurate in terms of like, because the last layers would also be using the updated weights of the previous ones?
So the question is, at training time, if we did this computation of the hidden states sequentially, wouldn't it be more accurate? The way that we've set up the self-attention equations, there's no difference if we do it sequentially or in parallel, because there are no dependencies between those hidden states. So if there were dependencies, then we have something like an RNN where we can't easily parallelize. Yes, it's a good question. Yes?
This is something on this, but for future, are we going to be talking about the bit manipulation within training?
You mean like quantization and things like that? Yes, we will get to that towards the end of the semester. Yes. No worries.
So for at test time, you said we don't know what the next word would be. So
Yes.
Why don't we? I thought.
So think about how you use ChatGPT, right? You using ChatGPT is an instance of ChatGPT at test time, right?
Oh,
Because
I see.
you have not, trained. It hasn't seen what you're about to
So
provide.
test
Right?
time is like inference.
Yes.
Okay.
Test time is inference.
Okay.
So when you go to ChatGPT, you ask it, write an essay about something, right?
Alright.
You don't know what the essay is ahead of time. All right. Okay, the other thing that we did not talk about is that the self-attention mechanism, the way I've described it, actually has no information about the order of the words in the sequence. So if you think about when I drew out the, favorite LLM is, so we had this embedding, and then I did my, query key value projection on each of these. Then I computed these dot products, but in no way, none of these steps did I inject any information about what position these words are. And so self-attention by itself doesn't have any way to encode position in it, right? So it doesn't know that is the last word of the sequence and favorite is the first word. So let me put that here. Self-attention requires injecting position info into the input. And so we will just talk about the simplest possible way of doing this, which is at each time step, before I compute these QKV projections, I will just add an embedding that is associated with the position of the word in the sequence. So this P1 embedding is the same for all words that are at position 1 of a sequence. This P2 embedding is associated with all words that are at position 2 of the sequence, and so on. This is probably the worst way to encode position into your model, and we'll have a whole lecture later, either next week or the week after, about better ways to encode position information, but you need some way to tell the model this word is in this position, this word is in this position, before you do all these computations. Otherwise, you get something that's kind of similar to the element-wise sum or average of the input, right? The order is not encoded. Does that make sense? Yes?
When you're encoding position, like how do you make sure that maybe embedding 1 plus the position embedding doesn't actually equal to another?
Oh, that's an interesting question. So the question is, how do you ensure that, like when I take my favorite word embedding and I add the embedding of position 1, that it doesn't like clash with another embedding in the vocabulary? In general, remember that all of these embeddings are real valued. They're generally like 100 or 500 dimensional. So it's highly unlikely that you would, I mean, impossible really, that you would get the exact same vector of another word. It probably could happen in a softer way, especially if the embedding dimensionality is reduced. But
Like, how do we make sure that the range of values for the embedding and the position embedding are different?
yeah, the question is like, do we kind of clip the values or have some sort of range associated with these? Generally, you will initialize the embeddings to be within some distribution, like a normal distribution or something, but and you might use gradient clipping when you're training to prevent it from blowing up, but yeah, not very common. In general, the embeddings just are whatever gets backpropped into them. Good question. Yes?
And what if the vectors of this like favorite and the other word that we saw in the cache are close, not exactly the same? Wouldn't that also cause a problem?
Well, remember that if we actually want the word embedding for favorite to be similar in this vector space to synonyms of favorite, right? So it's not like we want all the words to be as far away from each other as possible. But yeah, like initially during training, you'll get a bunch of random similarities that are not meaningful linguistically, but then over time, we will observe the separation. All right, let me check on here. Okay, now with all of that said, I guess, sorry, one last thing before we get into drawing more boxes is just a bit of terminology. So I mentioned one of the final project ideas of efficient inference is related to something called the KV cache. And so I wanted to just explain now what that is, and then I can highlight what it actually means when we go through the transformer. Basically, the KV cache is something that we're concerned about at test time, and it is associated with storing previously computed keys and values. So we don't have to recompute them at every step. And so this is relevant at test time. So basically at test time, we are computing the prediction of one word at a time, right? So at every step, we have to do all of these QKV computations to figure out what is the hidden state at the last time step that I'm at. And then I can feed that to my softmax layer to predict the next word. But I don't need to recompute all of the Q's and K's and V's of all of the previous words that I've seen in my prefix, right? First of all, I don't need the query vectors of any time step other than the one that is the last one at inference, right? And secondly, I do need the Ks and Vs of all of those previous things, but I don't need to recompute them. They're going to be the same every time. So generally what happens is we will store the previously computed key and value vectors, and we will reuse them at every time step. We'll be adding newly predicted keys and values associated with newly predicted words to this cache. And so you can imagine as your output gets longer and longer, like maybe 100,000 words you've predicted, you now have a huge number of Ks and Vs in your cache, because for every time step you'll have keys and values associated with every layer of your network and every head, which is something that we're going to talk about in a bit. And so the management of this cache becomes very important. And so, yeah, that's something that we will be touching on later. Yes?
So, for the same word, will the key value be same or will it be different? Like for the
That's a good question. So for the same word, let's say I have a sequence like, my favorite LLM is really the best LLM, right? So now I have LLM occurring twice. The question is, will the query and key, the key and value associated with LLM be the same in both of these cases, assuming we have like a one-layer transformer? So what do you think? Will this be the same?
I mean, we just said that we need to add position in positional.
Exactly. So the position is a big change, right? Because if they were the same, you would have no way to distinguish that one of them came early on in the sentence and one came at the end. So yeah, in general, like the way that we have described it in this highly simplified setting, they would be the same if we did not have any position information. But since they are the same at the very first, since we are going to add position, they become different. And then also you have, like, as you add more and more layers, they will start to look very different because at higher level layers, the input is not the word embedding, but the previous layer's hidden state, which is already different at those positions. Yeah, good question. Yes?
So then if you say we're caching the K and V values, the queries, the keys and the values, what exactly are we caching? So are we caching, like, for a given sentence, the part of the sentence that we've already seen is that?
Yeah, and the keys and values associated with that part of the sentence that we've already seen. Yeah.
So during training, you probably have to see like a lot of sequences.
At training, this is not a problem because at training, we can compute all of this at the same time, right? And so it only crops up at test time because we want everything to be as fast as possible. And yeah, yes?
Within the architecture, does the cache live within the transformers themselves or outside of the transformers?
That's a good question. So where is this cache? Generally, different libraries handle it differently. Like if you do it completely naively, then the KV cache will just be on the GPU with everything else. But that's generally not often the best way to do things. And so there's a lot of like offloading to the CPU and other very clever algorithms have been developed for this. Okay, let's move on, and then we could take more questions after I get through the topic for today, which will probably bleed over to next time, but that's fine. It is important. So now we're going to talk about the transformer, and self-attention is the critical building block of transformers, but as we'll see, there's a lot of modifications of it that make it a standalone language modeling architecture. So at a high level, this is a neural language model similar to recurrent neural network, but it's built on what's called multi-head self-attention. It's also not a single layer network like the one we looked at in the last class, but it's a deep network with many stacked, we'll just use an acronym, multi-head self-attention layers. And these layers are often in papers called blocks because one layer actually has a lot of linear layers and attention and feed-forward layer going on. So the terminology is a bit weird. If you hear someone say transformer layer, they're talking about everything from computing the query key and value to doing the dot product, softmax. Then, as we'll see, there's more complexity with the multiple heads that is all part of the block. And again, this architecture was developed in 2017 in a paper published at NeurIPS by researchers at Google. Okay, so I'm going to first just write out some high-level intuition that was, the one promoted by the original paper. It's not super clear how valid the intuition is, but I think it's still a good way of thinking about or understanding like what these researchers were thinking about when they built this architecture. So, intuition. So we talked about the query keys and values, right, that we project from a single input representation or like word embedding. The multiple head thing is just let's have multiple sets of query keys and values for each token. And so why might we want to do this? Well, then each set or head can learn to focus on a specific linguistic property. So, I might have a head that is more syntactic in nature and looks at all verbs in the prefix. So regardless of what the prefix contains, I might have one head that puts a lot of attention on each verb in the sequence. I might have another head that looks at all named entities in the sequence or all nouns or something like that. I probably don't want my only head to be looking at verbs, but maybe it's helpful to have one head that does something like this. I could have other heads that activate on certain words or phrases. So instead of looking at all verbs, I might have a head that looks for, some specific topic or some specific things related to a specific person or something like that. Again, very dependent on task. And one that's quite common is heads that focus on this class of like people or place thing names or dates, numerics. These are generally very useful for all sorts of tasks. So importantly, we are not constraining the model in any way that, okay, head 1 should learn the syntactic property, head 2 should focus on, this particular topic, and so on. We're just allowing the model to have these possibilities when it's doing this next word prediction task. Does that make sense? Yes?
If you don't have a strict idea of like why you're modeling it that way, doesn't that leave a lot of room for like overtraining or something like that, where like you're overtraining because your model's too complex?
So I guess your question is, this is just an intuition, but we don't actually know what is happening in general, so does that make our model too complex?
Yeah, like if you don't know what you're looking for, then say you have like, okay, why 12 and not 16, or why 12 and not 10, something like that.
Yeah, that's a good point. So like, how do we choose how many heads to have and how many layers to have? Again, these are all hyperparameters. If you look at the original transformer paper, they tried a bunch of different configurations with, there's actually a lot of hyperparameters. How many heads per layer, how big are the hidden dimensionality per head, how many layers do you have, how much data do you train on. There's no like clean way of saying this is the optimal architecture for this data. And so that's why really these kinds of papers are done by big labs that can blow a lot of compute to try out like, you know, hundreds of different configurations. But it's a good question. There's no good answer. Yes?
You have a different weight matrix for each of those.
Yes. As we will see, for each head or each set of QKV vectors, we will have a different parameter matrix WQ, WV, WK. So this is also a good way to get more parameters into your model.
But isn't that like exactly similar to having like a bigger weight matrix, which is just like a concatenation of all of them?
Yeah, the question is, isn't this similar to having a bigger weight matrix, which is just a concatenation of all of them? In fact, that's how it's implemented. If you look at the implementation of a transformer, you will generally do like one big projection and then split the result into the individual head vectors, because it accomplishes the same thing. But it's not the same, because once you compute the attention scores, you're only using each individual slice of those. So it's going to give you different attention scores for.
But then isn't the only point speed? Like we just want to pass all of them together, right? Like that's
Yeah, you can compute each head in parallel, which helps you. Like you're not, there's no dependencies between these heads.
what I want to understand is like how is this helping with the linguistics? Like apart from the speed, like what is this adding?
So again, the intuition is that some of these heads can focus on different properties of the prefix than others. So if you imagine a single head, it has to be very robust to all sorts of different linguistic properties of the prefix, right? So in some prefixes, maybe it's important to just, and I should add here, one big role of certain heads is to look at specific positions. And so it might make sense for a single head to always put a lot of attention on the last word or the last two words, right? Those are super important. But then you might want some heads to look more further back in the sequence, to be more position invariant. So yeah, these are all,
Extracting different embeddings for the same.
yes, for the same prefix, yeah, and the same token, yes.
Isn't it similar to having like multiple models for each layer? Like each layer is like different models, but you're combining their results to get like the
I mean, so the question is this similar to having multiple models for the same prefix that you're then like ensembling together? In some ways, you can think about this as like, we will see in a bit how you combine the information from the different heads. But again, the self-attention is just one module within this larger network. So I think that that analogy is, it makes some sense, but again, we're still working within the confines of a single model. So it might be a little more clear when we talk about how to combine the heads. Yes?
So we have like different weight matrices for each head.
Yes, different weight matrices for each head. I will just go through the equations and then, yeah, that'll probably be more clear. Any other questions? All right, I am happy to take as many questions about this as needed because it is very important that you all understand how this model works, since we're likely not going to focus on another architecture in the rest of this class in this much detail. So most of the stuff we'll do after this is based on this architecture. Okay, so let's get started with our favorite prefix, which is now, let me draw it down at the bottom. Favorite LLM is, actually I might want to do these more further apart. Okay, so here I'm going to draw two things just to make, kind of integrate what we talked about before. So here are my word embeddings, and then to each one I'm going to add this position embedding, so P1, P2, key 3. And note that you can literally do this addition, element-wise addition, or you can do many other functions. In many cases, there are no unique parameters associated with the positions, but we will talk about all of that later. For now, just assume that you're putting some sort of position information into these embeddings. Yes?
Sorry, just to zoom out for a second. So we were talking about recurrent neural networks and attention and stuff, right? But now that we're talking about transformers, my understanding is transformers don't use recurrent neural networks. So did we move past those now? Or?
Yes, so transformers are an alternative to recurrent neural networks where we can compute the hidden states in parallel, unlike RNNs. And transformers use self-attention, not recurrence. Yes, so those should be like a contrast to each other. All right, so we have accomplished this addition. And now the next thing we're going to do is our favorite QKV thing. So let me try and use the same colors I did before. This is going to be Q, whoops, K, A, and B. I'm going to copy this here. And now we're going to start adding some more notation because we're going to be making this a little messier. So this is Q1, and we're going to superscript it with the layer that we're on. So currently we're doing the first layer. Similarly, this is going to be K1, K2, and K3, and all associated with the first layer, and V1, V2, and V3, all at the first layer. And so now we talked about these computations as, let's say they're associated with head 1. So we're going to use, let's say Q11 equals F of WQ1 C1. So I have a weight matrix WQ1 that is going to be used to compute the query vector at every position of the first, for the first layer of this network. Yes?
Wait, why are all the query vectors the same?
Why are what?
All the query vectors the same?
Oh, sorry. Good point. These are not supposed to be the same. Okay, good. Other questions? Okay. So now let's do a second head. And so I don't know if I can reliably copy these. Maybe I should draw them again. Okay, and I'm just realizing that I was saying layer instead of head. I meant to say the superscript is associated with the head. So we've written out head 1. Now we are going to write out head 2, which is going to look like this. Okay, I'm going to copy this. The notation is not even going to allow for me to do multiple layers, but we'll give it a try later. Oops. Okay, and then I'm just going to add the 1, 2, 3, and 1, 2, 3. Okay, so now we have 2 sets of QKV vectors for each position in this sequence, right? And head 2 here, head 2 here is, if we're going to compute the query vector associated with the first position with the second head, all we're going to change is the weight matrix. So now we have a different weight matrix, W sub Q2, that is associated with the second head. Does that make sense? So similarly, we have a WK1, WK2. So we have 6 different weight matrices that are used to compute these 2 sets of QKB vectors. Okay, so that's great. And now we already talked in the last class about the self-attention computation, right? So for the first head, I'm going to, let's just say I'm at the 3rd position here. I'm going to compute the dot product between Q3 and all of the key vectors, right? Note that I'm not touching anything associated with the second head. I'm only operating within the first head. Similarly, the second head is going to compute this dot product using its set of query and key vectors. And so through that process that we talked about in the last class, we compute these attention scores, and we use them to take the weighted average of the value vectors, right? So at the end of all of this, I'm going to put that we're going to do masked self-attention instead of writing out all of those different computations. At the end of the day, we get the hidden states, right? The H sub 1, sub 2, sub 3. These are the result of computing this weighted average of the value vectors. The issue is here, we actually get 2 hidden states, right? We get H1 for the first head, and we get H1 for the second head. Here we get H2 for the first head, and H2 for the second head, and here we get H3 for the first head and H3 for the second head. So what we're going to do now is concatenate these 2 hidden states together. So we're going to form one larger vector where this is H11 and this is H12, and here this is H21, H22, and finally here H31, H32. And now we're going to pass this concatenated vector that contains both our hidden states into a feed-forward layer, or a linear layer, like we saw before in multiple different architectures. And that is going to give us our final output that is fed to the softmax. So we'll call this Z1, Z2, and Z3. Now, let's take a look just so that we're all clear on how this works. This is a linear or feed-forward layer. And so we can compute Z1 equals F of some new weight matrix W sub Z, and we're going to take our concatenation of H11 and H12. And here Z2 is going to equal of WZ times H2, H22, and so on. So you can see how this framework can be extended to an arbitrary number of heads, right? For each head, we need to have 3 new weight matrices for WQ, WK, WV, and we also will need to enlarge our W sub Z matrix in order to support the new head, right? Because the input to this feed-forward layer is the concatenation of all the hidden states from each head-specific computation. And just to complete this, at the end of all of this, we are going to feed this to our softmax layer to predict, what are we predicting here? LLM, predict is, and predict chat GPT. Okay, so that's a lot of boxes and arrows. Does this make sense? So we've extended from a single head to multiple heads. In doing so, we've also added this linear layer at the top after we've computed all the head vectors that's used to combine all of them into a single, generally lower dimensional vector. You had a question?
So, how do we determine the number of hits here and the number of dead heads in between? Like, is there any?
Yeah, so the question is, how do we determine the number of heads? Again, this is just a hyperparameter that you have to just try a bunch. There are some like kind of agreed upon conventions for generally you want to use powers of 2 when looking at the number of heads, but yeah, it's generally just what configuration gives you the best performance. Yes.
What's the intuition behind like introducing multiple heads for layers?
So the intuition associated with multiple heads is now that each head can focus on a different type of information found within the prefix. So if there's multiple types of information in the prefix that are useful for predicting the next word, you might be able to capture that better with multiple heads. That's the high-level intuition, but it's very hard to interpret the behavior of each individual head in practice. Other questions? Okay, so I think next we can talk about, oh, did you have a question?
Is there a dot about the comma of H11, H12, or is this your?
Oh, sorry, that's a semicolon indicating concatenation of those two vectors. Yeah.
So the below one is also a semicolon.
Sorry, yeah, so this and, oh, sorry, I didn't draw the, yeah, these are both semicolons. Did you have a question?
Are you using the value vectors in this?
Yeah, so when I wrote this masked self-attention thing down here, I just omitted the, when you compute these H11 and H12, those are the weighted combination of the value vectors. I just didn't draw it because it's too much to draw. Yeah. All right, let me check on YouTube. No questions. Okay, so now we're going to get a little more complicated and talk about what happens when we want to add multiple layers to the network. So as if it wasn't already too many boxes. So let's start down at the bottom here. This one hopefully won't be as annoying, but it will still be a lot of drawing. Okay, so I have my favorite LLM is. I have my C1, C2, C3, and to that we added the P1, P2, P3. And now I'm going to kind of abstract all of the computation that we saw in the previous slide into one box. So I'm going to call this masked multi-head self-attention. Okay? So everything that was on the previous page is now going into this box. And the outputs of this box are going to be my Z sub 1, Z sub 2, and Z sub 3. So to get these Z's, you can look at the previous page. That's what we're doing. Unfortunately, now we're going to have to introduce some more subscripts because this is just the first layer of our transformer. And so I'm going to put this up here to denote that now we're at the first layer. So now, if we want to make our network deeper, which we generally do, that's a good way to add more parameters into the network. And generally, as we train on more and more data, we want our model size to go up also. So now, what we're going to do is compute our query key value projections on these z vectors. So the input in the second layer is no longer the word embedding added to the position embedding. It's actually the hidden state, this z sub 1, associated with the previous layer. So the output of the previous layer becomes the input to the next layer. And in general, we're not just going to compute one of these, right? We're going to compute a bunch of these associated with each head. And so for each of these heads at the second layer, we have new parameter matrices, WQ, WK, WV. So let me just copy this and paste it. Okay, so at the end of the day, here we now will do our self-attention stuff, and I'm just going to write out what it looks like in practice. So here we might have the first head, the second head, the third head, fourth head, and so on. You might see networks with 16 or 32 heads per layer. So it's actually a huge number of parameters are being put into the computation of these heads. Same here, you might have H21, H22, H23, blah, blah, blah. H31, H3, oh, yeah, 2, H33, H34, and so on. So as many heads as you have, you're going to have that many concatenated together. Now we're going to compute another of these z vectors. So we'll call this z12. It's associated with the second layer of this network. This is, z22 and z32. And again, this, let's say z12 equals f of wz2 times this concatenated h11 blah, blah, blah thing. And so you can see that we actually have another feed-forward layer here for the second layer that's associated with combining all these head representations together. So now another concept that's associated with increasing depth in neural networks is this idea of a residual connection. So that means if we think about some of the issues with this setup, one thing associated with making your model deeper and deeper is, again, you have this issue with the vanishing gradient, right? It's a long path between the bottom of the network and the place where the loss is computed. So if I had like 100 layers, right, that's a lot of products in my partial derivative with respect to the bottom of the layer. And so one thing that was developed, about 10 years ago now, was this idea of a residual connection, which is actually very simple to understand. Basically, when you compute the output of your current layer, you're going to add that to the output of the previous layer, and that's going to become your new output. So when I compute z11, I'm going to take that and sum it with the input to that layer, which was the sum of the embedding and the position embedding. And then that sum is what I'm going to pass into the next layer as input. Similarly, when I compute z12, I'm going to add it to the input of the layer, which was z11. And so what this does in effect is introduce a shortcut connection for the gradient to flow, because in each layer, I could follow the gradient back through all the attention computations and the feed-forward layer and so on, Or I could take a shortcut and just follow it through the simple addition that's happening through the residual connection. So it really helps optimization in deep networks. So just to be clear, I'll draw it out for one of these. The input to my next layer is actually Z11 plus Z12. So I have added the input of the current layer to its output. And if I wanted to stack more layers on top of this, I could. So I'm just going to say now our final form of this box, which is hiding all of these computations, is masked multi-head self-attention. And now I'm going to put XL here, which indicates I'm going to have L layers of this. So at the end of the day, I'm left with my Z1L, Z2L, Z3L, and the very top hidden states are going to be fed to the softmax layer to predict the next word, which in this case, I have to go all the way back down here. Predict LLM, predict is predict chat GPT. So there's actually, more stuff that happens in a transformer. There's normalization layers that are happening at each layer, but we're not going to get into that. For this course, what you should focus on is what we've covered here, which are transformers are stacked blocks of masked multi-head self-attention layers, and we have these residual connections that are helping with the gradient flow as well. Okay, so at this point, let's take questions.
So when we do the addition for the residual part, do the two vectors have the same dimension?
Yeah, that's a good question. So when we're computing the residual connection, which is the addition of these two vectors, they have to have the same dimensionality. And so that generally the hidden size of all of these z's has to be the same in order to perform that operation. Yeah. But that's just, again, a hyperparameter of the network. So you decide in advance how big that is.
And so exactly how would it be helpful for the managing gradient?
So I probably don't have time right now, but if you just think about it intuitively, we start from the very top, right? So at the top of this network, maybe I can use this orange color. We compute the loss, right? When I predict ChatGPT, we talked about how we compute the loss, which is like negative log probability of ChatGPT given this prefix. And so now, if I wanted to backprop normally, I would go here, I'd go here, I'd go into here. And now, if I didn't have this residual connection, right, I would backprop into this network, into this hidden state. I'd have to go into this concatenation of all the heads. Each of these heads has some, is a combination of those value vectors, which themselves is a function of the QK dot products, right? And so I have to go into all of these. And finally, then I get to the bottom of this layer. So there's a lot of computation involved within a single layer to get to the next layer down. It's a lot of matrix multiplications, which could lead to the vanishing gradient issue. So if I had a residual connection, on the other hand, at this point, like right here, I could decide to go down here, or I could take this shortcut and skip all of that stuff that's happening inside that layer and go straight to the next layer. So in practice, the gradient splits into both of these directions, and the idea is that this residual helps prevent the gradient from vanishing because you can get to layers that are further down without so many intermediate matrix multiplications. Yes.
Why is the Z12 there?
Where?
Like for the state,
Like right here?
the circle one.
So here the superscript stands for layer, right?
Yeah. Sorry. This is why the notation is very annoying. So I've used superscript for head in the previous page, and here I'm using it for layer. So
that's the second hidden layer then?
yeah. So this Z is the second layer of the transformer network. Up here, the H superscript is the second head of this single layer.
Okay.
Yeah.
Oh.
Yes.
Why are there a different number of heads between different layers? Like here there are 4 heads.
Sorry. That's just for demonstration. So in this case, because I had to draw out everything, I just had 2. But in practice, you're going to have much more than 2. It's usually 8, 16, 32, something like that.
Is it a fixed number of heads between each layer, or are there?
Yeah,
different-
generally each layer will have the same number of heads. There are some works that try and vary this, but
Then the
yeah.
parameters would increase.
Yeah, exactly. So to keep it simple, I mean, it's not simple, but to keep it relatively simple, we'll have same number of heads per layer. Yes.
So we encode position once, and I guess it's remembered throughout the rest of the network.
Yeah, that's a good question. So as you see here, position is only encoded in this network at the very bottom, and we could have like 100 layers until we get to the softmax. But yes, the thing is that the model only needs it once if it's trained properly. Yes.
When we do the residual back propagation, do we also do the other way back propagation so that the weights in the hidden sections will also be updated as well as the residual?
Yeah. So I want to emphasize that the shortcut is not, like, both paths are backpropped through. The shortcut is just to kind of help with the vanishing gradient problem.
But
Yeah.
With the updated of the 2 paths, they would also lead to the same result?
No, because the second path, the one that's not the shortcut, you have to go through the actual computations happening in that layer, which, you have to expand out the chain rule. You'll have all of those intermediate products. Yeah. Other questions? Yes.
Yeah, just like a small mapping. Isn't the case that the chain rule will always lead to the gradient becoming smaller?
I mean, it depends on the eigenvalues of these matrices. So it could lead to them exploding as well if they're always getting bigger as you multiply. But in this case, like, unlike the RNN, you don't have the same matrix that's being repeatedly applied, so it's a little less clear. Again, I would encourage you, if you're interested, to read the paper that introduced residual connections. It's from 2015. It gives a very good empirical support to why these things are important. Yes? The linear layer. So you mean like going from the H's to the Z's? So that's a great question. Actually, when you have a very deep transformer, most of the parameters are in this WZ matrix that's associated with the feed-forward layer here. The reason is you might have 32 heads. Each head might be like 100 dimensions or something like that. And so the dimensionality of this WZ matrix is actually quite large, because it might be like, 10,000 by 100 or something. So you get a lot of parameters into the network by having this linear layer. Like, you could go without it, but then your output of this layer would actually be of a pretty large dimensionality, because it's concatenating all of these the H's together. So it acts to like reduce the dimensionality of the concatenated head vector, and also as a place that you can add more parameters to the model. Okay, so in the next class on Monday, we will talk about, at a higher level, what are all the different ways that we can use a transformer? So currently we've been talking about it as a next word predictor, but there are many other use cases that all differ from each other in how you mask the attention. And so we will cover that in the next class along with pre-training and fine-tuning. So see you then.